table sorted with respect to one digit. And then we kind of ran out of time, and I thought I'd skip it. But now, given what we're going to be doing next, I thought I'd spend a few seconds on it anyway. This is called radix counting sort, where the input are in numbers, each L bits long, and you want to sort them. And what you do is you break them into blocks, the bits into blocks, and you consider each of these blocks to be a digit. All right, so now this is just like radix sort, where you have so many digits, and each digit's within some range. All right, and then you can use counting sort to sort with respect to the low order digit, and then the next digit and the next digit. Everybody kind of follow that algorithm? And we don't need to go through the details. This is just what I said about the running time. It's an example that's in the book. But if you kind of work out the running time, it comes out to that the running time is L times N. Right? You have N numbers, each with L bits. And the number of, and what's the size of the input? Well, you have N numbers, each with L bits each. Right? So the size of the input is L times N. Right? So, and we call that's the number of bits in the input. And so what's the running time in this input? Is it linear, exponential, quadratic, in log n? It's linear, right? Because the running time is within a constant of the size of the input. All right? So this is called the linear time sort. How many of you have heard in the past that sorting takes n log n time? All right? So if you're like me, when you hear that there's a linear time algorithm for sorting, in fact, what we're going to do next is we're going to prove that sorting takes n log n time. All right? So now it looks like we have an algorithm that takes linear time. Then that's, anybody know what's going on here? All right, so the catch, what's the catch here? Well, so here we're sorting n numbers, each with L bits, right? And merge sort, it takes, we're saying that the running time of merge sort is n log n, right? Where we call the size of in order to sort n numbers, right? So that's what we're going to prove in a minute, is if you're doing some sort of comparison test, yes, no questions, then it takes n log n time to sort n numbers. Well, how does that compare to this? Well, L is probably, if you have n numbers and they're distinct, then you need at least log n numbers to describe each of them. So L has to be at least log n. People follow what I'm saying here? Right? So really these running times are the same. Right? If you want n distinct numbers. Right? So it's not really a contradiction. It depends on it's n log n time. Well, what's n? Is n the number of bits to write down the input, or is it the number of numbers? So that's the difference. People kind of follow that? Doesn't really matter. Quite frankly. Now we're going to now prove a lower bound. Maybe the last slide started here. All right. like that little box. All right. So we haven't, in this class, looked at merge sort, quick sort, or heap sort, but you've seen them in other classes, and they take in log n time. Have you seen anybody ever seen a lower bound proving that you can't do it any faster than that? Did that guy do that in your class too? Hope he didn't use my slides.
You have a tree where
actually my previous version had a tree, and I redid my slides, so maybe he has my old slides. All right, so these are my new slides, and the reason they're here is because this is the last thing we're going to do in the loop invariant section. And what we're going to do is we're going to come up with a new algorithm using loop invariance. All right? And what's the algorithm? Well, let's first study our first order logic. All right? You all should, even if you think you know first order logic, you should look at the section in the back of my book on first order logic, because my bet is most of you don't know it. In fact, I teach the grad course, and most of them don't know it. All right? So the way I like to think about first order logic is you read it from left to right, and it's a game between an adversary who's trying to prove that it's false and me, or the prover, who's trying to prove it's correct. All right? So we read it from left to right, and when you see a for all, you're trying to prove for all algorithms something is true. Right? We want to prove that something is true for every algorithm. So we get the adversary to give us an algorithm. Right? And this algorithm, what's this algorithm? It's claiming to solve sorting of n numbers in less than n log n time. All right, so the adversary gives us this algorithm that claims to solve sorting in less than n log n time. And then we see an exist here, so it's my job to come up with the I. I come up with an input, right, and I give it to the algorithm. And then who wins depends on whether this is true or not. All right, so I win if the algorithm that the guy the devil came up with doesn't give the right answer on my input, right? Because I proved that his algorithm doesn't work, right? I also win even if his algorithm gives the right answer, if his algorithm takes too much time, right? If it takes n log n time, then I win. Everybody got the game here? Everybody sort of see first order logic? So the game is, so I need to come up with an algorithm now. The input to my algorithm, this is a little bizarre here. The input to my algorithm is going to be what? What am I given by the world?
An algorithm.
I'm given an algorithm, right? So the input to my algorithm is an algorithm. It's a description of an algorithm. And what is the output of my algorithm?
Numerical or
no.
An input. The output to my algorithm is an input on which the algorithm I'm inputted, the algorithm A, either gives the wrong answer or takes too long. Right? Does that make sense?
Or can you go over that again, because I was lost.
Yeah, for sure. Good on you for asking. All right? Our goal is to prove that no algorithm that just sort of does yes-no questions, comparison-based questions, bit questions, can sort faster than n log n time. Right? And how we're going to do that is, this is going to be me, and I'm going to run some algorithm. And what's this algorithm going to do? I'm going to get from an adversary his best go, his best possible algorithm A. Right? He's going to give me an algorithm A, And what I'm going to do is I'm going to come up with an algorithm I, and I'm going to show either that the algorithm he gave me gives the wrong answer, it doesn't correctly sort, or I'm going to show that his algorithm takes longer than n log n time. Right? Now I claim that this, if I could do this, it would prove that there is no such algorithm. Right? Why? Because if there was an algorithm that could sort in less than n log n time, then he's going to give it to me. Right? And if he gives it to me, then I will fail to come up with an input. Right? If he gives me a correct algorithm, then this correct algorithm, what does it do? It gives the right answer in the right amount of time for every input. Right? And hence, I will fail at coming up with an input on which it either gives the wrong answer or takes too much time. Right? Right? Because the contrapositive, the flip, the negative of this would be there exists an algorithm such that for all inputs, the algorithm gives the right answer and the algorithm runs in the right amount of time. Right? People know how to take the negation of a first order logic statement. Right? The negation is you take the negation, you change for alls to exist. They're such that for all I, now we have to negate this. Well, the and turns into an or turns into an and, right? And not equals turns into equals. So AI equals PI, and the time is less than or equal to. Yeah.
Yes.
Exactly. Right? This is a statement which says there is an algorithm that works fast on every input. Right? This is the statement that says there's not such an algorithm. Right? Everybody good with that? And so now my goal is given an A to find an I. Right? Everybody good with what our goal is? And what am I going to be? I'm going to be an algorithm that uses loop invariance.
What's the whole point of like trying to find an algorithm that is fast enough? Like, because can't you just make the condition like arbitrary? Like, can't you just make the time that it goes faster than like really slow? If you can, or like, I mean, are there requirements to like deciding the conditions, or because I mean, what is it supposed to do?
Right. All right. Well, if I put a 10 there, is this statement true?
Yes.
Does there exist an algorithm such that on every input, the algorithm gives the right answer? Well, this is the problem, sorting. I don't know if you got that. This is the output of the algorithm, and this is sorting. Right? It gets the right answer in n log n time. Do you think this is true?
No.
What if A and B were the same algorithm?
A and B? I don't see a B.
Oh, P.
Isn't an algorithm, it's the problem. Sorry, I didn't say that. Maybe that confuses everybody. Let's start over. So P is the problem sorting. So it's the answer of sorting. I give it an input, it says what you want to output. And A, you give it an input, the algorithm, you give it an input and it's supposed to correctly sort them. Right? So this is just a way of writing down the algorithm is giving the right answer on input I. Right?
And for example, like, is I a set of numbers or something just to see if it can sort properly, or is it something else?
No, I is the set of numbers to sort.
Okay.
Right? It has to be in the right.
Yeah.
Otherwise we wouldn't be able to put this. Right? Everybody should know whether this is true or not. Can you sort it in log n time? Yeah, you can. For example, merge sort, right? Quick sort, heap sort, right? It always gives you the right answer, right? And it does it in this much time. All right? So this is a true statement. Now I'm going to change this 10 here to, I don't know, a tenth. Is this a correct statement? Right? Does there exist an algorithm that always gets the right answer and can sort using 1/10 in log n comparisons? What we're trying to prove here is that this is not true. Right? You can do it in 10 in log n, and you can't do it in a 10th in log n. And you know what the exact constant is here? I don't really know. We can play with it and we could figure it out. But
Like, is it just so that in order to test if the algorithm is good enough, or because I still don't understand the concept, or why you see the problem with the algorithm.
well, I guess the purpose of lower bounds is not that then we can do something better, right? This isn't going to help you do anything better. It's going to help you understand computer science, understand computation. You want to know, you might want to know, well, how fast can one sort? Right? So in order to know how fast one can sort, you need to know two things. You want to know, I can sort this fast, and it's impossible to sort faster. Right? So we know we can sort in 10 log n time, and we want to prove that you can't sort any much faster. Right? You can't sort faster than a 10th in log n time.
Okay, so you would have no idea what to make the time. Like that would be like trial and error.
Well, I mean, if you don't care about constants, and we could play with the constant if we wanted to, then we know how long it takes to sort. Right? You know you can't prove it you can't do it any faster.
Yeah.
Right? Did you know that you can't do it faster? Maybe there's an algorithm that can sort in time. How do you know there's not an algorithm that can't sort in square root of n time?
Also, is it to compare like algorithms that do similar things? Or?
I mean, like for the factoring problem, if I give you a number, an n-bit number, and I want to factor it, it takes, the best known algorithm I think is something like this much time. Right? And people would really like to know that you can't do it any faster. Right? Because if you could do it faster, then that would be exciting. And if you could prove you couldn't do it any faster, then everybody who's doing cryptography would be happy because they know that their cryptography is safe. Right? And in terms of sorting, I don't know, it's just a fundamental question of computer science would be, how long does it take to sort? Right? We know we can do it in n log n time, but how do you know you can't do it? Maybe you can do it in, right? I mean, do you think it's at all possible you could sort in this much time? Why not?
You have to look at these.
You can't even look at the input in this much time, right? There, what he just proved a lower bound. He just proved that you can't sort in this much time, right? Can you sort in this much time? Well, at least you have time to look at the input,
Yeah.
right? So we're going to prove that you can't sort in this much time.
So like right now we got like dual cores or quad core. We could look at the import in 4 different spots at the same time. So does that make sorting faster?
if you have lots and lots of parallel machines working, then yeah, they'll do it faster, but the amount of work, the number of comparisons, the total number of comparisons won't be less, right? Because you have all these people working in parallel, right? So if you're asking, if I'm going to, you know, I have 1 million processors all working together, and I sum up the work that each of them does, they won't get any faster than this. The reason they're faster is because they're sharing the work. All right? So people understand, you know, I'm given this algorithm A and I want to come up with an input in which it either gives the wrong answer or it takes longer than 1/10 over n log n time. And I don't know, are people getting this? Does it matter how long I take to work? My algorithm? No, because I'm just a theoretical mind machine, right? We're never going to implement me, right? All right. So let's see what we can do here. Come on.
Lost connection.
Why are you shutting me off?
Oh, here we go. All right. So sorting. Let's remember what sorting is. Sorting, the input is a bunch of numbers. And just to make our life a little easier, we can add on that comes with every number comes with an index. And then the output is you sort them, and the indexes get sorted along the way. All right? And the lower bound, right, as I said, we're given this algorithm as an input, and the output is going to be an input, right? Which the algorithm either takes too much time or gives the wrong answer. And we're going to use loop invariants to describe what I do. All right? So, right, the adversary, he gives me an algorithm and claims that it sorts fast. And then, right, my goal is to come up with this input. The first thing I'm going to say is, well, all that really matters to me is the order in which the numbers appear. Right? So I'm going to just assume that the numbers I'm trying to sort are 1 through n, and we're just trying to sort the indexes. All right? Now, here's sort of a funny problem, is I need to know what this algorithm does, right, before I can decide what input it's going to fail on, right? Right, because this algorithm might do really well in some inputs and really badly on other inputs. So I have to know what it does before I choose my input, right? But the problem is, I need to give the algorithm an input before I know what the algorithm does, right? So this becomes this circular argument, right? How do I know what this algorithm he gave me did? You know, I don't even have it in my hand here, right? I want to know what is this algorithm going to do, but I don't know what it's going to do until I give it an input. But I don't know what input to give it until I know what it's going to do. You see that sort of circular argument? So what we're going to do is we're going to break the cycle. Think about this one time step at a time. All right? We're going to have a loop invariant which says, remember we had a bunch of types of loop invariants, and one was restricting the input domain. Right? Restricting the search space. Right? So my loop invariant is going to say, well, I'm only going to consider inputs which are permutations of the numbers 1 through n, and I'm going to keep a subset of the permutations. Right? These are all possible inputs. This could be an input, I give the input. You know, these are all possible inputs. And my loop invariant is that this guy's algorithm, for the first t time steps, he does exactly the same things on all of these inputs, right? If I gave him one of these, he doesn't know which of these inputs I've given him until, like for example, he has to look at them, right? I mean, until he looks at it, until he plays with it, he doesn't know enough about these which input it is. Right? Does that make sense? Right? On all of these inputs, this algorithm will do the exact same thing for the first t time steps.
What do you mean t time steps?
Well, I have some number t. You know, maybe we're working on the 7th time step, right? We're at the top of my loop. I've gone around 7 times.
Oh, okay.
I have a set, and right, he's going to do the same things for the first 7 time steps.
Okay.
Right? Everybody kind of got that?
How do you figure that out?
Well, it's my loop invariant. I asked the fairy godmother for it, and she gave it to me. Now my job is to maintain it while making progress. Right? And I have to establish it at the beginning, and I have to get the postcondition from it at the end. Right? So initially, I put in here all in factorial, all the possible inputs here. They're in factorial possible permutations. Right? And t is 0. Right? So what he does for the first 0 time steps is the same on all inputs. Right? Why? Because he hasn't done anything yet. Does that make sense? Everybody with me here? All right. So that's how we establish the loop invariant. You know, we're going to have a measure of progress will be the number of inputs that we have in this set. Right? So we have in factorial so far. All right, now we have to define our step. All right? Now, during the first t time steps, what he does on all of these inputs is the same. Right? But on the t plus first time step, he can do something else. Right? So what is he going to do in his t plus first time step? Right? And all of these inputs, what he does after the first t time steps is fixed. So the action he takes on the t plus first time step will be the same for all of the inputs. Right? He's going to take that same action. And what will that action be? Well, he might compare, you know, he might compare the 7th value to the 2nd value. Right? He might ask, all he's allowed to do is bit things. Right? We charge him for bit operations. He might ask, is the 5th bit of this sum, is it 0 or 1? Right? He asks the question. Or he can ask any yes/no question. You know, think about it. You know, a lot of you probably know the game 20 questions, right? And that's probably the tree he had. He had James had the tree of 20 questions. No? All right. So anyway, everybody kind of get the things he can do here? So what I do is I go over here and I look at each of my inputs and I see, oh, look at on this input, the answer to this is yes. On this input, the answer is no. On this one, it's no. On this one, it's yes. Right? And so I partition these inputs into 2 sets. Such that on all of these inputs, whatever he did in the t plus first time step, the answer to his question was yes. And to all of these, the answer to his question is no. Right?
If you have same 2 algorithms, the same input, and the same loop invariance, there's a different runtime.
2 algorithms with
Same loop invariant,
but
different runtime.
Yeah? You have different exit conditions. Everybody see how we partition this into 2 sets? And now what do? What do I do now? I want to maintain the loop invariant.
Do you try again for t plus 2?
Yeah, but I haven't quite gotten the loop invariant for t plus 1.
You have to pick one of the sets.
I choose one of the sets. I narrow my set down to one of these sets. Right? Because then that maintains the loop invariant, because what he does for the first t plus 1 iterations will be the same for everybody in here. And which side should I take?
Yes.
The bigger one. Alright? I take the bigger half. And then at some point, I don't know if I said that, the number in the set, right, goes down by a factor of 2 each time. So after t iterations, it goes down by a factor of 2 to the t, right? And then I guess this, right, that maintains our loop invariant for t plus 1. Really good? And, or measure progress, here it is, right? We started off with, that was supposed to be a capital N, that many permutations, right? It goes down by a factor of 2 every time step, so after t iterations, we have at least that many inputs left. Everybody good?
Why this part is larger than the other one?
Why is it bigger?
Yeah.
Well, it's just how many inputs. Right, we partition based on his question, and they could be exactly the same size, in which case we choose either of them.
Okay.
Right? One of them, would you agree that one of them is at least of size a half?
Yeah.
Right? So that's all we're saying, is that at least one of them is the size of half, and if they're the same, it doesn't matter which one we take. And that's why it comes down by a factor of 2 each time. All right? And then when do we exit? Well, when we exit, when there are 2 instances left. Two of these inputs left. So, how much time does it take? Right? We start off with in factorial of them, and every iteration comes down by a factor of 2. So the number of these iterations that we can do is the log base 2 of in factorial. People get that? And in factorial, let's think about what in factorial is. In factorial is 1 times 2 times 3 times 4. It's the number of permutations, right? Why is it the number of permutations? Well, you have to choose who your first number is going to be. There are n ways of choosing it. Choose your second number, n minus 1 ways. Everybody with us? This is the number of permutations. And what is this number? Well, it's pretty close to n to the n. Right? Here, it's at least n over 2 to the n over 2, right? Because we have n over 2 numbers which are bigger than n over 2. And it's bounded above by n to the n. So it's about that. And if we take the log of it, if we take the log of this, then the n comes down and you get a log, n log n. Everybody good there? So that means we can continue this game for n log n rounds. Right? And now, from our exit condition and our loop invariant, we have to get our postcondition. All right? So what is our postcondition? Is I have to come up with an input on which an algorithm either takes too much time or gives the wrong answer. Right? That's my postcondition. Remember my loop invariant is I've narrowed it down to 2 inputs for which this algorithm is doing the exact same things for t time steps. Right? And if this algorithm doesn't stop after the t time steps, right? Then I can prove that right, the exit condition, it takes that much time, so it takes too much time. Does that make sense? Right? If his algorithm doesn't stop after this many time steps, then I win. Right? Because I have 2 inputs on which he takes more than that much time. Right? Everybody follow that? Conversely, suppose that he does stop and he gives some answer. Right? Now, I don't know, I was looking at these slides on the way here. I don't know why PowerPoint is being weird, but it is. We have 2 inputs, and these inputs have different answers. Right? They're different permutations, so he's supposed to sort them differently. Right? But he does the same things on these 2 inputs. So he gives his algorithm gives the same answer on these 2 inputs. Right? But they're supposed to have different answers. So on one of these inputs, he might give the right answer. Right? But on at least one of them, he gives the wrong answer. And we're done. Right? Does that make sense?
So say they get to that point and there are two inputs. One of them stops right there, and the other one stops 2 steps ahead.
Well, then we're good because the one that took too long took too long.
Oh, yeah.
We're good? All right. So this just says for every sorting algorithm, there's a worst case input in which it takes n log n comparisons.
So our algorithm always gives them 2 outputs to do. Right?
Yeah. Oh, well, and at the end we'll choose between them to say what. Come up with one of them gives the wrong answer,
Okay.
and it gives the one that gives the wrong answer.
Okay.
Right? Now, as a theory person, one of the things I've spent a lot of time doing is trying to prove lower bounds, and they're really hard to prove. And the community has proved very few lower bounds. I don't know if you've ever heard of the thing called P times N versus NP. That's what it's trying to prove, that you can't solve certain problems in polynomial time. And people are really not good at it. All right, that is the end of loop invariance. Any questions about loop invariance? We're now completely done loop invariance, which means not next Monday, because then you wouldn't give you enough time to study if you wanted. But the Monday after, I'm going to give you a brand new question. I'll say, here's the input. This is what you expect from the input. This is what you expect from the output. Now give me an algorithm, right? And what are you supposed to do? Are you supposed to give me code for that algorithm?
No.
No. Oh, you guys are very good. What are the steps? Someone want to tell me the steps? Specification. Do you have to do that one? Well, I probably did it for you, right? The question will say the pre and post conditions. But yeah, the first step that you have to do is you have to be damn sure you know what the precondition is and what the post condition is. You have to read the question very carefully, right? Then what should you do? No, I wouldn't do that first. Loop invariant. You want to tell me, this is my loop invariant. And in a nice clean paragraph with a nice picture maybe, you tell me what the loop invariant needs to be. Right?
Does the order of the step matters?
No, there are different orders you can do it in. But a lot of the steps depend on what your loop invariant is, right? You can't maintain the loop invariant before you tell me what your loop invariant is, for example.
Yeah, because on the book, the second step is actually define the basic step. So.
Yeah, in the book does a lot more hand wavy than what I want you to do on the exam. All right. So what the book does is it says, think about this and think about this. Right? So it has the first step is not actually to give the steps, but think about your basic steps. Right? So yeah, as far as exactly as I've taught this course more and more times, I'm more and more focused on telling you exactly what I want, so to increase the probability that you give it to me. All right? And what's in the book is an earlier iteration where it's not quite as clear. All right? So first thing I would do very clearly, tell me what the loop invariant is. Right? And then
Maintain loop invariant?
Then a fine thing to do would be how do I make progress while maintaining the loop invariant? So to do that, you have to tell me what steps you will take first. You say another paragraph. What steps am I going to take? You say, hey, I'm from Mars, I'm on the top of the loop. This is all I know is that I have some data structure that meets the loop invariant. Right? What actions am I going to take? Right? Then you have another paragraph which proves that the loop invariant is maintained. You say I'm at the top of the loop, I know the loop invariant is maintained. let I prime and S prime be the values I have of my variables when I'm at the top of the loop, right? I know the loop invariant is true with respect to those variables. I come around the loop, I do the code, which tells me the values of the variables S double prime, I double prime when I've gotten back up to the top, right? And I know the relationship between I prime and I double prime, right? And now I need to formally prove that the loop invariant is true when I come back to the top again, right? And what do I mean by formally prove? It just convinced me, Say something that's at all reasonable, right? If you've done everything else there right, the proof will just kind of be reasonable, right? If you think about all the examples that we've done here, right? It won't be harder than any of those. Right? Everybody got that? Now, the other one is making sure that you make progress. Right? What's my measure of progress? And make sure you make progress every step. Usually that one's really easy. Right? But sometimes, and if it's really easy and you forget to say it, I won't take off any marks. And if it is actually hard and you didn't say it, then I will take off marks, right? So you have to kind of at least think, hey, is this obvious? Right? And if in doubt, at least say, hey, we have a measure for progress and we make sure we make progress. Put the word progress there, right? So I know you got the step. You can say, clearly we make progress because I increased by 1, right? That would certainly do it. Right? Now, what do we need? What's the last thing we need? Oh, we need an exit condition. And officially you need the exit condition before you can do the progress and maintain the loop invariant, because if you've already exited, then it's harder to make progress and maintain the loop invariant. But, usually we can hand wave that one a bit. All right, so we define an exit condition, and what should the exit condition not be?
Postcondition.
You guys are good. It should not be the postcondition. If it's the postcondition, then it makes the last step really easy, but it makes it too easy. It makes the exiting much harder, right? You have to then prove your algorithm's going to exit. So the last step is you get the postcondition. How do you do that? You say, I know the loop invariant is true, right? That tells me this about the data structure. I know the X condition is true. That tells me this about the data structure. I maybe have to do a little extra work, but probably nothing too hard, right? And from that I conclude that the postcondition is true. Everybody good? Little paragraphs. Oh, how about that? How perfect is that? We don't have to start recursion. Any other questions about anything? How many people are in a place of panic? Ish. How many people feel that it's doing okay? Good. So, maybe we can get you all to pass the test.
What if everyone passes the test, we all get perfect?
Life would be good. I don't see any problem in that. In the end, if more than a third of you get an A, I will have to write a letter to the powers to be and explain why it happened. Right?
Don't make this course any harder.
And I'll tell you, I've been teaching this course, and if it was the first time I ever taught it, they might balk at that, right? But I've taught this enough times that if I really said, I don't know what happened, they all got an A. They give it to you. I'm a tenure professor. What are they going to say?
Make your course harder.
I have a sense of how well you guys can do. If you all get an A, I would be very happy. In fact, if you all pass it, I'd be very happy.
On average, what's the average people that fail. No, the whole course.
Oh, the whole yeah.
I'll tell you what I don't keep track of. And I feel guilty that I haven't kept track of this. I don't keep track of how many people drop out. Right? So I don't know how many people ever dropped out. But in terms of people who write the exam, a few years ago I would have said a third of them deserve to fail. But I passed all but 1 or 2 of them. In the last few years I really felt everybody deserved to pass. And